I need to make a revision, actually an addition to that video I just posted on core options trading strategies part 3, where we go back to the basics and define the values of tranches. As I was looking at the video after I posted it last night, I realized that I left something out, and that's going to cause problems if you're trying to follow the logic of this. Now, it's not so much of a big deal. You'll see what the addition is here in just a minute. But if you're trying to logically figure out how to calculate the value of a call option by integrating off of the log normal distribution, then the omission would be a big deal. So I apologize for that. If I were editing this video, it would not have happened, because you catch these kinds of problems in an edit before you ever post it. This is one of the drawbacks of live streaming. The videos sometimes have omissions, or they have problems that you somehow have to figure out how to fix. So the supporting slide set has had this slide added, and a couple of comments changed on the other slide. So let's see what I'm talking about here. Let's get to this. Okay, this is the original slide in the slide set that I presented yesterday. And this is where we broke the original stock distribution, which again is a log normal distribution, into two tranches separated by the strike price. So nothing changes about this video. We go down to the bottom comment there and we say if our model is good and this tranche is priced at the value of our model, then this is an example of an efficient market, and that remains true. But then 2 slides or 3 slides after that were misleading. This is the slide that I'm adding. There's a difference between the tranche value and the call option value in this example. The tranche value is represented on the left and is as I represented it in this slide set, but I think I even said that this represents the option value as well. That's not quite true. Take a look at the abscissa on the added portion of the slide where it says this is the call option value, and you can see the abscissa has shifted from the strike price being at 435 to the strike price being at 0. And here's why. The tranche is not the call option. The call option is a special contract that gives you the option of buying the tranche at a price that is equal to the strike price. And so therefore the actual value of that contract has to net out the cost of engaging in the contract, because of course the call option that we're talking about here gives you the right to buy the call at 435. And so the call option is equal to the tranche less $435. Now, mathematically, all that means is we shift the axes in this mapping there, and you convert that from the tranche value to the call option value. And if you were integrating, you would make a similar adjustment, of course. So the result in the call option distribution is shown on the right side of these two. The upper axis shows the payoff, and the cumulative density function, which we're not mapping, we're showing the probability density function. And so therefore the area underneath that represents the value of the asset in question. So for the tranche, the entire tranche is worth that integration underneath that probability density function, and the call is equal to the one that's on the right. Now, of course, that should make some sense, because you ask yourself, well, what if it turns out that the stock price actually goes to 435? And the answer is, well, the call is actually worth nothing, because that's where this starts. But if it goes up to, say, 437, then it is moving from 0 to 2. If it goes to 487, then you have moved from 0 to 50. And so, therefore, of course, it's worth $50 in that case right there. So if you want to know the probabilities of getting that range past the strike price, then this upper axis on that integration is the way you do that. So, and the lower axis is just as there for reference to show the price array associated with the payoff. So the actual payoff is indicated by the upper axis. the price array associated with where that zero actually is represented more or less on the bottom axes. Now that means on this slide, it makes sense to change the axes as well. There's nothing else about this that we really have to say, because what I said about the tranche is true. If your tranche is priced efficiently given market conditions, and you should assume that it is, and if this condition is typical of all tranches that you price, you have no reason to expect profits by virtue of trading these tranches. And then if we convert this from a tranche mapping to a call option mapping by simply changing the axes as we do here, because effectively that's how you do it, then the same thing is true when you talk about the value of a call option. And furthermore, once again, if you can find model-based evidence that this option is mispriced, and that's the mistake I made. I referred to it as an option in this slide, whereas I referred to it as a tranche in the other slide. And the original was a tranche and not an option, but here now we have both. On the other hand, if you can find model-based evidence that this option is mispriced or this tranche is mispriced, even if momentarily or perhaps because of a deficiency in someone's model, then if you trade correctly with that information, profits become profitable. So again, we're qualifying this to say that's true for the tranche, and there's no tranche trading out there, although the tranche has value, and you need to calculate that, for example, when you do something like write a covered call. That's later. Now we are making ourselves clear about what this means. And we say, is this call inherently more valuable if we write it instead of buy it? And again, we actually need to be referring to the value of the call and not the value of the tranche. And so the upper axis where the red arrow is pointing is valid. It's also valid for the tranche if you're talking about pricing it. And the fact that it has a premium is not relevant. And finally, for the put, this is the odd unadjusted mapping. So we said, oh, this is effectively a put. But of course, it's a put only if you account for the fact that you have the right to sell your option for $4.35, and that would be a cash infusion into your account. So the abscissa that's appropriate for the put value is the bottom one there that starts at 0 and grows larger as you go to the left. Now again, you can still integrate that, but you have to change the way you do the integration. Obviously, one way to do that is to mirror this, and then of course the values would be rising. There's various ways to do this. So for the abscissa, if you take 435 and subtract the values along the original abscissa, then you have the April 24, 435 put. So the upper axis gives us the tranche, and the bottom axis gives us the put. It is worth its integration value, and again, you would have to integrate reverse or mirror the image and integrate normally to actually accomplish that, which is not all that hard to do. So those are the qualifications that we have to make. We have to convert the tranche to an option before we can talk about it as an option. I just left that out because I was in a rush to get the video out. Apologize for that. But now, if you go back and look at the slide set, it should be understandable to you. So, all right, we'll wrap that up with that comment.